For this lesson, we'll take a look at lesson 8.3, which is about testing a claim about a proportion. We have three learning targets here. First, check the random and large counts condition for performing a significance test about a population proportion. So both of these conditions should be correct, should be met for you to be able to perform a significance test. Second learning target is to calculate the standardized statistic for a significance test about a population proportion. And the third learning target is to find the p-value for a one-sided significance test about a population proportion using table A. So get ready with your table A. We will be using that today. Now, how do we check conditions for performing a significance test about the proportion? Okay, so this is not new. We have discussed this before. The two conditions are, is it random? Does the data come from a random sample from the population of interest? And then the second condition is it large counts? Is the large counts condition met? Okay, how do we know it's large counts? Both n times p, the sample size, times the population proportion, and sample size times n minus p should both be greater than or equal to 10. Okay, let's have an example. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was P equals 0.63. To reduce this proportion, the manager assigns an additional employee to assist with drive through orders. During the next month, the manager will collect a random sample of 250 drive through times and test the following hypotheses at the significance level of alpha equals 0.10. So the null hypothesis is the p is equal to 0.63, and the alternative hypothesis is that p is less than 0.63. Taking note that p represents the proportion of customers who had to wait longer than 2 minutes. During the next month, the manager collects data on wait times from a random sample of 250 drive through orders and finds that only 141 of the customers have to wait longer than 2 minutes. Check if the conditions for performing the significance test are met. So first condition is it random? Okay, so in the problem, it says that the manager collected a random sample of 250 drive-through times. So random sample of 250 orders. Okay, so that checks out. Now the second condition is the large counts condition. So is the large counts condition met? Okay, we need to calculate NP. N is the sample size. The sample size is 250. And the proportion is 0.63. Okay, 250 times 0.63 gives us 157.5, which is greater than 10. And N times 1 minus P is equal to 250 multiplied by 1 minus 0.63, which gives us 92.5, which is also greater than 10. So both conditions are met. Okay? So pause the video and try to work on the next problem. Okay, so for this next problem, is it random? What part in the problem tells us it is random? Okay, it says here that Jason chooses an SRS of 60 students. So Jason chooses an SRS, oopsie, of 60 students. So the random condition is met. Okay, second, the large counts. So is the large counts condition met? You have NP, which is N is equal to 60. Sorry, N is equal to 60. And P is the proportion of 0.80. And that gives us 48, which is greater than or equal, greater than 10. Okay, let me just get the extender. And the second one, okay, N minus P, N times 1 minus P, sorry, is equal to 60 multiplied by 1 minus 0.80, which gives us 12, which is also greater than 10. So both conditions are satisfied. And if both conditions are satisfied, then that means that you can proceed with calculating the significance test or doing the significance test. Okay, and that's what we're going to do next. Okay, so we will do calculations of the standard test statistics and the p-value. So get ready with your table A. Now, what is a standard test statistic? It measures how far a sample statistic is from what we would expect if the null hypothesis were true in standard deviation units. In other words, we will convert the standard um, raw score, the raw data, into a z-score or a statistic into a z-score. So you have had this before. Okay, so this is your z-value, right? Um, let us review what the z-value would entail. So this is basically z is equal to, that's the standard test statistic, the z-value. It's equal to, since we're testing the proportion here, your statistic is the p-hat. Okay? Now, the null value is the mean of the p-hat. And then you have the standard deviation of the p-hat, standard deviation of the statistic. Okay? Now, we know from 6.4 that the mean of the p-hat is basically equal to p. The mean of the proportion, sample proportion, is equal to the proportion value, okay? The population proportion. And then the standard deviation of p-hat, we have the formula right here. It's equal to the square root of 1 of p multiplied by 1 minus p divided by n. Okay, so we'll be using these formulas to calculate the standardized test statistic. All right, let's take a look at example number 2. So this is still the fast food example. Okay, so you still remember this. We want, so during the next month, remember that the manager collected data on the wait times from a random sample of 250 drive-through orders. Now, out of the 250, he finds that 141 of them have to wait longer than 2 minutes. Okay? So your statistic in this case is the p-hat, right? So what's our p-hat? P-hat is 141 over 250. Okay, to alleviate the error in calculation, we'll just turn this into decimal. Okay, but you want to make sure that you do the rounding correctly to 3 decimal places. So 141 divided by 250 will give us 0.564. Okay, so that's your p hat. That's this one. Now, mu of p hat, which is your null value, is equal to p, right? Now, your p here is equal to 0.63. Okay. Now, as for the standard deviation of the statistic, we have this formula, right? So we'll just plug in square root of p. P is 0.63. And then 1 minus p is 1 minus 0.63, which is 0.37, divided by n. Our n here is 250. That should be included in the square root. So putting everything here into the calculator, um, we will get 0.031. Am I right? Okay, let me double check. So square root of 0.63 times 0.37 divided by 250. Okay, so that's 0.03053, so that's equal to 0.031. Okay, so we calculate the z. We're not done yet. I should have made more space here. Okay, so our z is equal to the p hat. P hat is 0.564 minus the mean of p, the p-value 0.63, divided by the standard deviation 0.031. So 0.564 minus 0.63 divided by 0.031 will give us negative 2.13. Okay. Now, we'll find the p-value using table A. Now, what is table A? What does it give us? It gives us the area to the left of the normal curve, right? So let's draw our normal curve here. Okay, so we have our normal curve. And now I want you to, so that you know which area to shade, which area we want, you take a look at the alternative hypothesis. So the alternative hypothesis here is less than, which means, okay, let's first plot the z value. So z value is negative 2.13. So it's right here. This is your negative 2.13. Now, which part do we shade? Left of 2.13, negative 2.13, or right of negative 2.13? Again, it depends on the alternative hypothesis. Since your alternative hypothesis is less than, it means that we have to shade the left side. Okay? And the p-value is that shaded portion. So here is your p-value. So looking at table A, our p-value is the probability that z is less than negative 2.13, okay? Which we can read off from table A, and that is equal to 0.0166. Is that correct? Negative 2.13, negative 0.0166. So the p-value is 0.0166. Okay? So the first thing we did was to calculate the standard deviation, okay? And then we plugged in the values into the formula for z to standardize the score. And then we constructed our normal curve, and make sure that you shade the correct region. Now, the correct region, you shade the correct region depending on the alternative hypothesis. So if it's less than, you shade on the left side. If it is greater than, you shade on the right side. Okay? Because remember, in this particular unit, we are only doing one-tailed. Okay? Either the left or the right. So what conclusion can be made here? Now remember from the previous lesson, we will have to compare the p-value. In this case, our p-value is 0.0166. We will compare that with the significance level alpha. So what significance level did the manager choose? Okay, alpha is equal to 0.10 right here. Okay, so we compare the p-value with the alpha, and based on this comparison, we'll draw our conclusion. So we say that because the p-value of 0.166 is less than, right? Is less than alpha, which is equal to 0.10, then that means that we reject the null hypothesis, which means that there is convincing evidence for HA. What is our HA? That the true proportion of drive-through customers who have to wait more than 2 minutes is now less than 63% or 0.63. Okay? Now, what happens when the data don't support the HA? Okay. Supposing your HA in this particular case is that the proportion is less than 0.63, right? Now, however, now it just so happened that the calculated p-value here, or p hat, is 0.5664, which is really 0.63, less than 0.63. Okay, so your statistic supports your alternative hypothesis. 0.564 is less than 0.63. So we can proceed with calculating the significance test, okay? However, say for example that you got a p hat that's equal to 0.66. Now, 0.66 does not support your alternative hypothesis, right? Because 0.66 is not less than 0.63. So there is no need to continue with a significance test. So you just have to take note of the comparison between the statistic and the alternative hypothesis. The statistic should support the alternative hypothesis. Okay, now let's put them all together. Okay, so this is just a short lesson. So let's take a look at this. On TV shows that feature singing that on TV shows that feature singing competitions, contestants often wonder if there is an advantage in performing last. To investigate, researchers selected a random sample of 600 college students and showed each student the audition video of 12 different singers. Each student viewed the videos in random order. We would expect approximately 1 out of 12 of the students to prefer the last singer scene, assuming order doesn't matter. So in this study, 59 of the 600 students that were chosen at random preferred the last singer they viewed. Now we want to perform a test at the alpha equals 0.05 significance level of these two hypotheses. So our null hypothesis is P is equal to 1 over 12. And the alternative hypothesis is P is greater than 1 over 12, meaning they prefer the singer that they have seen last. Okay? So P is the proportion, true proportion of college students who prefer the last singer they see. All right. So the first step when you perform a significance test is to check the conditions. So again, the two conditions are, is it random? Okay, so from the problem, it says there that researchers selected a random sample of 600 students. And you would want to always specify where you see the randomness. Researchers selected a random sample of 600 students. So that checks out. And then the large counts. Okay, we want to calculate NP. N here being 600, and P is 1 over 12. And that's equal to 50, which is greater than 10. And then our N, 1 minus P, is equal to 600, 1 minus 1 over 12, which is equal to 550, which is also greater than 10. So the large counts are met. Okay, we can proceed. Okay, so we will calculate the standardized test statistic. Okay, what is our p hat? This is our statistic. What is our p hat? It says in this study, 59 of the 600 students preferred the last singer they viewed. So p hat is 59 out of the 600 students. And that is equal to 0.098. Okay. Now, mu sub p hat is equal to our p, which is 1 over 12. And 1 over 12 in decimal is 0.083. Now, we calculate the standard deviation. So the standard deviation of p hat is equal to the square root of formula p, 1 minus p, over n. Okay? So let's plug in. Our p is 0.083 times 1 minus p. So 1 minus 0.083, that's equal to 0.917 divided by n. Our n here is the 600 students. Okay, so just to make sure, this will give us square root of 0.083 times 0.917 divided by 600. That is 0.011. Okay. So now that we have these values, we can calculate the Z statistic, the standard test statistic, which is equal to the score, which is equal to what? 0.098. That's your statistic, minus your null value, your mean, 0.083, divided by the standard deviation, which is 0.011. Okay, and this should give us 0.098 minus 0.083 divided by 0.011. It's equal to 1.36. Oh, and by the way, let's compare first. Okay, the statistic is 0.098. Okay, is 0.098 greater than the p-value 0.083? It is indeed greater than. So our statistics supports our alternative hypothesis, right? 0.098 is greater than 0.083. So we can continue. I forgot to check that earlier. Okay, now we find the z-value, the p-value, I mean. Okay, so let's draw our normal curve right here. Okay, so your z-value is 1.36. That's on the right side, okay? This is your 1.36. Okay, which part do we shade? The left side of 1.36 or the right side? So in that case, we have to refer to our alternative hypothesis. Alternative hypothesis is greater than, which means that we need to shade the right side. Okay, so this one here, the shaded portion, that is our p-value. Now, how do we find the p-value? Now, remember that in table A, the given values in the table is the probability of the left side. Okay, so the p-value is equal to 1 minus the probability that z is less than 1.36. Okay, because z is less than 1.36, this is what's given in the table. So that would be 1 minus, so if you look at table A, 1.36 is 0.9131, which means that our p-value here would be equal to 0.0869. Let me just double check. 1 minus 0.9131, yes, 0.0869. That's our p-value. So how do we make the conclusion? We will compare the p-value of 0.0869 with the significance level. So significance level here is 0.05. Okay, that's your alpha. Okay, so again, your p-value is greater than, right? So because the p-value of 0.0869 is greater than alpha equals 0.05, then what is our conclusion? Then we fail to reject HO. Okay, we fail to reject HO, and we say that we do not have convincing evidence for HA, right? So we do not have convincing evidence. Okay, so HA in context, HA is the proportion, that the true proportion of students who prefer the last singer is more than 1 over 12. Okay? Which means that basically there is no advantage to singing last. Or performing last. Okay, so there is a last problem here, number two of putting them all together. So your homework is to work on this problem here, and we will discuss this the next time we meet.